Hello everyone and welcome back to another video. In this video we'll be teaching you how to program the clock in C, which works with either a raw chip or an Arduino. And in a later video we'll show you how to program using the processing programming environment. So hope you enjoy.
Welcome to Daddy and Daughter Electronics episode 5. Where we are continuing to make our cool clock. What's on this breadboard are wires that are connecting this raw chip to these resistors and to this ribbon cable that is connected to our clock. This is ground and this is 5 volts.
Where can I get the schematic for this circuit?
The schematic for this is in the source code.
What size are the resistors?
Whatever size resistor you need for the color you use needs to be divided by 2 because one resistor is on the plus side and the other is on the minus side. When you first turn it on, it starts circling like what it's doing right now. And then when it's done, it does that. It's kind of hard to see. How you can see it better is you simply put a piece of paper on top of it. As you can see, it says 12 o'clock. Why does it say 12 o'clock is because we don't have the buttons yet to set the time. We'll talk about putting in the buttons in a future video, but for now we're just wanting to start small.
Now we're ready to talk about our source code. So here I have the source code for our clock. So what we've done is we've written a simple program. It's written in C. Now, some of you that are familiar with the Arduino might know processing, and then let me tell you a little secret. Processing is nothing but C anyway. It just has some nice built-in functions and things like that. So why didn't I use processing? I didn't use processing because for some things it's very slow. Now, it turns out that the Arduino doesn't really use lines. So if you've used the Arduino at all, you're always programming and you're setting a line high or low, input, output, etc. But actually the chip on the Arduino, the AVR chip, is using ports. And what happens when we use the ports directly, our program becomes a lot simpler for our Charlie plexing, and that's what we've done here. So here I start out by including some basic stuff, and there's some notes. So if you've been looking for a schematic, this is the schematic. If you use an ATmega 328 chip, you don't need a chip this large in order to do the clock. I just happen to have some of them around. So here you can see that we have the power connected to pin 7, ground pin 8, and then our Charlie plexing lines start here on pin 14 and they work their way around to pin 19. And here is a picture of the back of our clock. We've shown you this before in handwritten form, and here it is in the code. Now, every segment is mapped using 2 bytes. So the first byte says this line is high. The other part of this mask is a bit mask for the DDRB register. So you might say, well, what is that? This is the register that determines what is input and what is output. So if that bit is set to 1 for a certain line in the port, so of course every port can have up to 8 lines, then that is an output. Otherwise, it's an input. Remember from our earlier videos that if you have an input, that is a high impedance, a high resistance. So it's like disconnecting the wire. So what we've done is we've mapped out all of the LEDs. So we've said, okay, this is the line that has to be high. Line 1 has to be high. And here it has to be set as an output. The other line that has to be used as a low line has to be an input. So here's how to read this. The less than is a shift operator. So this says shift this one place to the left. So that's the same thing as saying line 1 has to be high, and here this says line 0 has to be low. For the next segment, line 0 has to be high, and line 1 has to be low, etc. And then we define what each of these segments in our 7-segment display mean. By the way, I've used the standard, where these are all standardized. A means the top, etc. And here we've set up all of the numbers. So this says this is the segments for the number 0. I go all around the outside. Here's a number 1, etc. Then I set up some more variables. A lot of these variables are called volatile. Volatile means that it changes a lot and it gets put in a special high-speed area on the chip. You have to tell the chip what speed you're going to run at. And we're running at 8 megahertz. This is my update frequency. 50 times a second, I will update the clock, and I have to tell it how many segments are on the clock. So I will go through each segment. I have an interrupt frequency. So at 1250 hertz, or 1250 times per second, I will cause a function to be called an interrupt. And I also define a couple of convenience functions to delay a certain number of milliseconds, to illuminate a segment using its what has to be high value and the DDRB, that mask, and it looks like this. I have another one for illuminating the colon, and I have a helper function to update these segment variables. So I have hours and minutes, and hours I store the current time in seconds since 12 o'clock or noon, and here I say the current time, hours equals the current time divided by 3600, because there are 3600 seconds in an hour, last I checked. If the hours are 0, then we set the hours to 12. The minutes are just the time divided by 3600, the remainder of that. That's what this does. And that divided by 60. That gives us our minutes. And then here we have what's displayed in each of our segments. Here we have our little function that gets called, and this gets called 25 times each time the clock gets updated, and it's updated at 50 hertz, 50 times a second. So every 1250 passes, we update our seconds counter. Now, really, there are only 24 segments, but I show the colon twice because if you divide your number by 24, it doesn't come out evenly, and we want the clock to be accurate. The clock segment can be 0 to 24. The digit is just the segment divided by 7. And then here I say, if it's more than or equal to 23, show the colon. Otherwise, it's a different digit. I load the appropriate mask, and then I set the digit. Notice I did something strange here for the highest digit, which is just a 1, and I added 1 to the segment because there is no segment in the first spot. Here, I set things to output and set pins high. If the current segment is not illuminated, I just dim everything. I increment my counter, and again, if this counter equals 1250, then I've gone for an entire second, and I add to my time, and if my time's greater than 43,200, which is the time for 12 hours, then I reset my time and I update my digits. Here's our power on self test. All it does is spin through the digits, as you saw. Here's our main function where we set up various timers on the AVR chip. And right now, we don't have a lot going on here. We just say delay in this while loop. It's an infinite loop because we will later put our button handlers in here once we've added the buttons. So that's pretty much it. That is our program. In a future video, we will show you the process of actually programming the chip if you have a standalone chip. You could also use an Arduino, of course.
So I hope you enjoyed the video, and tune in next time for when we upload the actual program onto the chip.